There. My audio's good now? Okay. All right. I guess I could back up a little bit for our captionists. So at first I started talking about the beginning, the beginning of the universe and man looking up at the stars. I talked about the big question when you look in the stars and you wonder where did all this stuff come from. And I talked about the first observatories and the idea that you want to take data in order to find out more. And like I said, you can learn things about the position of the Earth and the movement of the sun, the different transitions that the sun goes through. Like you could see here that you've got the solstice, like fall, the winter and summer solstice, where the sun will actually set between certain pillars in Stonehenge. And by doing that, there was a tool back then where they were able to use that to figure out when to plant crops, when to harvest crops, things like that. So it was very useful. But also it told a lot of things about like where we are in the solar system, how the solar system moves. And you could see in this bottom picture, there's a guy actually taking data. So there are actual records coming from this. Now, this led to more technology, which was needed for even more data. So you've got more accurate telescopes. You've got some telescopes even in space. And all of them are meant to study further and further out in the universe so that we can get a better picture of what's really going on in the universe, where all this stuff came from. So to put it all together, that really comes down to physics, not so much astronomy. So astronomy, a lot of that was based around the idea of these observations, at least classically. The physics part was actually saying that we're going to make a few assumptions about the universe from all these observations, and based on that, we're going to have this big understanding of the entire universe. And this works at both the large and the small scales. So, of course, not everybody understands what the theory is, as Johannes kept saying, you see the orbit of a planet is elliptical. And the first guy asks, what's an orbit? The second guy asks, what's a planet? And the third guy asks, what's elliptical? So it's like, this is also, the usual problem when you're trying to communicate science. So basically, this is the entire history of the universe. We start off at the top, where humans are out looking out at the stars. And we see all these stars, and if we go back a little bit, we see galaxies. And we see all these distant galaxies. If we look out further, eventually you'll get to the part where there really weren't galaxies and there really weren't even stars. About a billion, this is at 13.7 billion years nowadays. So if we go back about 13 billion years, there weren't even galaxies. They were just formed. You go back a little bit before that, you don't even see stars. You just see gas, like all this plasma bubbling around. And you go all the way back to 500,000 years after the universe began, and you can't see anything. And that's because everything was so opaque that you can't see before that. This is actually where the cosmic microwave background radiation comes from. And you'll hear physicists talk about cosmic microwave background radiation as basically the oldest signals from the early universe. But the truth is, it wasn't really that early because the universe was already 500,000 years old when it came about. So that's not really early. And in order to figure out what happened before that, you have to use your physics. You can't even observe any further than that. Because what happened was the cosmic microwave background, it's a radiation that kind of bubbled out from this opaqueness. And we're still seeing it today, and from that we're getting all these ideas about how the universe expanded and how the universe expanded, how the inflation happened, all this other stuff all these other theories about the universe, it all comes from here. before that, in order to see what the physics was like, a lot of that comes from experiments involving plasma physics and particle physics. So you have, let's say, this era of nuclei, where there were plasma, where you were just starting to form the nuclei for light elements like helium, and there's a lot of electrons floating around. Before that, you had nucleosynthesis, where you didn't even have these nuclei floating around. And then you can go back further to where you just had the elementary particles, quarks, antiquarks, electrons. You had this electroweak era, which before that the electric and the weak forces were actually combined into one force. Before that, you had the strong force all combined, possibly with gravity, into one grand unified force, which we don't even understand. And before that, we don't have a clue. So the only way to even get back here was all just going through physics and just making some assumptions and kind of looking at it. And the weakness of that is that it's just better to see stuff. And so if we could actually see what happened there instead of doing a lot of guesswork based on what we know about physics and assumptions, then that might be better. And so that's one of the things that gravitational waves can actually do. Because what happens is, if you look at this picture of the universe, again, you could see the entire history of the universe, and you could see that the universe was much smaller back then. But you could see at the very end, there's a light, kind of the light at the end of the tunnel. And right then was what we call inflation. And that was probably, in a lot of ways, I say, the most important event in the history of the universe, because that was when, according to our physics, the universe expanded by many, many, many orders of magnitude in a fraction of a second. It's like something going from the size of an atom to the size of a beach ball instantaneously. And we don't exactly know how that happened, but there's signals from it. And we think that we can infer some of that from the cosmic microwave background radiation, but we don't really see it directly. And so you can't really see it here, but this is basically a ball. And in an animated GIF, this thing will kind of wiggle. And you'll see like that's the ripples of the gravitational waves going. And so the idea is that when this inflation happened, that should have been a source of gravitational waves. And that could have been a source that we could even see today if we have the right tools. So what are gravitational waves? Well, like anything that starts with relativity, it starts with Einstein. So what happened was in about 1916, he comes up with this theory of general relativity. The basic idea of relativity is that, the speed of light is the same for every observer. And as a consequence of, you can actually, as something gets closer to the speed of light, the physics changes. And so, you can end up getting some really interesting effects like time dilation and length contraction. The interesting thing to me about the theory of relativity that he first came up with in 1905 was that at the time, we had Newton's theory of the entire universe. Newton was considered like, the biggest man on the hill, practically a god to all the physicists. And you don't question somebody like that. That's just the way science always seems to work. So Newton basically had a theory that worked out pretty much everything in the universe. Pretty much 90-something% of everything that had ever been observed could be explained by something that Newton said or wrote. Around the time Einstein was born, he was still little, this guy named Maxwell shows up. He comes up with this theory of electromagnetism, which explains the electric and magnetic forces. The problem is that Maxwell's theory was not compatible with Newton's theory. And so every sensible scientist on the planet, especially everybody who had a tenure track appointment, was working on ways to make Maxwell's equations compatible with Newton's equations because they knew Newton was right and Maxwell, he's new, so he couldn't be right. Einstein had nothing to lose, so he did the exact opposite. He tried to make Newton's equations compatible with Maxwell's equations, and it worked. He was able, if you read his paper, his 1905 paper was actually on the electromagnetism of moving bodies, or something like that, he called it. And so that laid down the relativity theory, and that made his, that really created his career. And so then about 10 years later, he wanted to apply that same theory to gravity. And what he came out with was that if you allow space-time to curve, then you could basically explain gravity within this context of relativity, of a kind of a fluid space-time. And so the way that works is basically, if you take a bowling ball, everybody uses the bowling ball example. By the way, a lot of these pictures I did not draw. I stole them from Kip Thorne and one of his presentations. So if you take a bowling ball and you put it on your bed, what happens is you'll notice that it kind of, causes an indentation in the mattress around it. If you take another smaller ball, it'll tend to roll towards that bowling ball where it's curved. The idea then is he's thinking that, well, matter curves space-time the exact same way. So if you take a piece of matter like a star and you put it somewhere, it's going to curve the space-time around it, and then anything smaller like a planet is just going to orbit it. It's going to roll towards it. So that's the whole basic idea of relativity. And so basically his theory was that space-time is going to tell matter how to move, and matter is going to tell space-time how to curve, and it's going to be the symbiotic relationship between the two. And then if you take this matter, your bowling ball on the sheet or on your mattress, and you roll it and you move it, what's going to happen is that curvature is going to have to change as you move the object. But that's not going to instantaneously change. So there's a way you could possibly make ripples in it. So you could actually create these ripples in space-time. And when you can do that, you create these ripples, then you create waves, or which are basically ripples. Then if you could actually see these ripples, then you could actually learn something about the matter that was moving. So it's a really neat idea. And then it's like sometime later, I think it was like around the 1930s, Einstein wrote a paper which completely disproved his theory of gravitational waves. And so that was the end of the story. Except for the fact that that paper was never published because it was actually rejected by a physical review. And that was when peer review of journals was new. And Einstein got the rejection letter for his article, and he responded pretty much how you would think most people would. He said, "I'm Einstein. What are you doing? Who you think could review this?" And the editors held fast, and they said, "No, with your paper, we can't publish it." And they ended up not publishing it, and he later on figured out this paper was wrong and gave up on it, and never published in that journal again. But that was one of the things that actually really saved the whole gravitational wave thing, because if that paper had been published and people believed it, we probably wouldn't be having this talk right now. So black holes are these things that can form as a result of the space-time. And these things are geographic anomalies, like were basically geometric anomalies, I guess is the better word for it. Because the thing is that like a black hole is where you've curved space-time to a point so extreme that the diameter is actually greater than the circumference of the circle. In other words, to go through the circle, actually is further than going around it. I mean, and the space-time curvature is so weird that it actually works out that way. And so you can create these objects, which are basically these, they're extreme curvatures in space-time, and they manifest as just very, very heavy objects. And so the neat thing about black holes is that when they first came out with the theory of black holes, the response of astronomers were that that's the stupidest thing I've ever heard. And then the astronomers realized something really interesting. If you take these things and you put them in the middle of all these little phenomena that they've seen but they can't understand, it pretty much explains a whole lot of them. And so then astronomers were like, well, we love black holes. That's the greatest idea ever. So you could see here as an example, we have these things called X-ray binaries, where they would just see this source of X-rays coming out of nowhere. And what's happening is a black hole is orbiting a star, and it's actually material from the star is getting sucked off into the black hole. And as the material falls into the black hole, it goes faster and faster and faster. And the light that it ends up emitting ends up in the form of X-rays, because they continuously get, as they fall in, they get more and more blue shifted because they're going faster. Another thing you can get are these active galactic nuclei. They would see these huge radio jets shooting out of galaxies, and they couldn't understand why that was until you say that, well, there's a supermassive black hole in the middle of it. Another thing is, you would see these spinning material, and a lot of that can come from spinning black holes, which is actually what caused the active galactic nuclei. Material falls in, but it picks up so much angular momentum that it shoots out. And then there were these huge mystery gamma ray bursts. Nobody knew where they came from. Nobody knew what caused them. Nobody knew why they were existing. All they knew was that there would just be these huge flashes of gamma rays. And if you looked at it purely in the gamma ray spectrum, they were like shooting out more energy than like the rest of the visible universe combined in just a few instants. But nobody knew what was causing it till about a year ago. So this is something that was like a huge, huge question. And they felt like, well, that's probably got something to do with black holes. So what does this have to do with gravitational waves? Well, you got this black hole, which is a really, really massive thing. And if you take a really massive thing and you move it through space-time, it has a massive curvature of space-time. And as it moves, it twists the space-time around, and the space-time stirs up. And so that is what's causing the waves. So the waves are basically the result of all of this movement, all this space-time getting stirred up. And then, so if you use black holes are just a great source of gravitational waves for this exact reason. Now, I gotta pause to let you know something here. When I was in graduate school, we were working on modeling the collision of black holes, particularly as a source of gravitational waves that they would hopefully one day detect. Well, the reason why we were modeling black holes was because they were a really strong source of gravitational waves. We had no idea how you could even get two black holes together. There was a lot of speculation for years about how many of these things could you even see, given a really great range on a gravitational wave detector. How many black hole collisions were there actually out there? We don't know. As far as we know, happens once every 100 years, and we just missed it. So we couldn't, so there's a lot of speculation on that. There was no real understanding on why the physics would allow two black holes to be close enough to collide. So let me see. Hopefully this works. Thank you, Windows. All right. This is where my flash drive comes in. Okay. So I think the first movie I want to show you has to do with the collision of two black holes. So you could see here, whoops, this is galaxies, not black holes. That one. Not that one. Well, this is close enough. Well, here you could see there's two black holes, and what's happening is they're spinning around each other. And this is a little bit unequal mass, but you can see that as they get closer and closer and closer, the waves keep changing in both the magnitude and the frequency. And then they get faster and faster and faster, and they whirl in, and then poof. And when they merge, you get just a single black hole at the end. So this was, like I said, I didn't actually do this simulation myself, but this was pretty fascinating. Here is a simulation of black holes producing gravity. This is the one I was looking at before. So here is another one. And again, you could see black holes spiraling around each other. And these little arrows are showing how much curvature you could see in the space-time. And again, at the bottom, this is actually what the waves look like. So you could actually see the change in the waves and their wavelength. So you can see the wavelength and the amplitude changes as they get to each stage. And they come together. And as they keep coming together, you notice they're going to move a little bit faster and a little bit faster. And now you can see they slowed it down so you could really see the merger. And then at the point where they touch, this is where the merger phase is. And they actually end up forming one odd-shaped black hole for an instant. And then they eventually ring down into just a spherical black hole. And when that merger phase is actually the higher amplitude phase, so that's the part where you can actually really see it the best. So, those are just two examples of black hole mergers. The other thing that's really massive in the universe that can be a good source of gravitational waves are these things called pulsars. And I think everybody's heard of these. But the basic idea is that you got a neutron star, and this neutron star has a magnetic field. And the neat thing is sometimes the magnetic field is not aligned with the axis of rotation. So what happens is that as the magnetic field whips around, you see a changing magnetic field. And from your electrodynamics class, you know that that looks like a electromagnetic pulse. So you see this regular pulse from this magnetic field whipping around. And it's just a little changing magnetic field. And that's why we call these pulsars. So these pulsars also can emit gravitational waves if they're close enough, because they are really massive. Now, the neat thing is, in 1974, what happened was Taylor and Haas actually found a binary pulsar system, whereas pulsars, or a pulsar and a neutron star, and they were close enough together to where they were orbiting around each other. And what he was able to do was, by looking at the pulse and looking at the changes in the pulse very regularly, you could see that the orbit of the neutron stars was changing. And since these are pulsars, not like regular stars, they don't emit optical light. So there's no other way for them to shed energy outside of emitting gravitational waves. And so what they did was, because of the way they were losing energy, they did the calculations and found out that they were losing energy consistent with the emission of gravitational waves. And that was the first indirect detection of gravitational waves. If it wasn't for this detection, they would have probably never funded a gravitational wave detector. So this earned them the Nobel Prize in 1993. Now, I want you to just take a note here. They made the discovery in 1974. They won the Nobel Prize in 1993. That's almost 20 years. That's actually how long it normally takes if you make a huge discovery to get a Nobel Prize. So keep that number in mind. Now, this is another movie which I think I'm going to have to exit out to show you. Has to do with neutron stars. So if I can show you, yeah, equal mass binary neutron star. Come on. Oh, there it is. So you can see here, we've got two neutron stars, and they're just kind of spinning around each other. Just let me start at the beginning. And you could see that in this simulation, as they get close to each other, they're starting to kind of take material off each other, but then they're emitting gravitational waves. So this is kind of what Taylor and Haas saw, but they didn't actually get to see the waves. They just saw that something else was going on here. And that something else was consistent with the gravitational wave. One thing you should know about physics is that a lot of what we do really comes down to probabilities, and the idea that it just seems more probable that there were gravitational waves than any other explanation. So here's another one. You can see these two stars. They're rotating around each other. Again, they're getting a little bit faster and a little bit closer. They're starting to merge, and when they merge, out come all these waves and all this big explosion. It almost looks like you're frying two eggs at the same time while you're spinning the pan around. Anybody else do that?
They rarely explode like that.
Well, when I make eggs. Okay. And here's another one. This is in spiral of, whoops. This is two neutron stars again. And they're in spiraling. And you can see they start to touch here. And they're merging. And then that's the connection. And then this is the last I'll show you on this stuff. These are unequal mass binary neutron stars. So they've been able to do all these different simulations where they just change some parameters. Like you'll see that they can have two equal mass black holes. They can have one black hole more massive than the other. They could have one neutron star more massive than the other. They could have a neutron star with a black hole. You could do pretty much any combination of that. And the nice thing is once you do a computer simulation, you can see all the data pretty much everywhere in here. All right, so it's a simulation I tried to show you. So what are other sources of gravitational waves? Well, first off, we talked about binary black holes, basically a pair of black holes. We can also have binary neutron stars, which I talked about. Now, these are things, like I said, the neutron stars, we already knew that they could form in pairs since Taylor and Haas. The binary black holes, they were just a very strong source, but we didn't really even know that they could be in pairs until we actually saw them. And then another source is supernova explosions. Every time a star goes supernova, that could actually send out a pulse of gravitational waves, because it's all you need is a lot of mass moving really fast, and you get gravitational waves. And then there are what they call stochastic sources, like, for example, from cosmology. And this would be like the background gravitational waves from the early universe is a good example. Like from inflation in the early universe, it could send out gravitational waves that would still be, ringing around in the background of the universe, just like the cosmic microwave background radiation does. And then we can get into exotic sources, and this is where the cool stuff happens. This is all like the physics that, like, you have to be really, really on a theoretical side to see. And there are things like cracks in the fabric of space-time, like cosmic strings. You can have surface cracks. You can have naked singularities. All this stuff that we don't really know exists. We can't rule it out. We can't say it's there. We just know that in theory it could exist. So what do gravitational waves look like? Well, this is the interesting thing. When a gravitational wave passes by, you can imagine you have a ring of particles like I show on the board. What happens is, as the gravitational wave passes by, the ring can get shorter and fatter and then taller and skinnier, and it's kind of flipping between those two. So if a gravitational wave hits you, what's going to happen is when the gravitational wave comes by, you're going to get a little bit shorter and a little bit wider, and then as it passes, you're going to get taller and thinner and keep flipping between those two. And that's assuming the gravitational wave is actually coming right out of the screen. Or you can have a cross polarization where it forms like an X. And so you can see the plus polarization forms a plus like this. And you can even combine the plus and the cross polarizations, and you'll have like what will look like an ellipse that'll just be rotating. So it looks like just a rotating ellipse. And so the neat thing is that just like electromagnetic waves have a polarization, gravitational waves can have a polarization. And we might even be able to find some information from what the polarization is. So the difference between gravitational and electromagnetic radiation is that you could see here on the two columns, I have the electromagnetic radiation on the left and the gravitational on the right, where electromagnetic radiation are basically oscillations in the electromagnetic field, and they propagate through space-time. In other words, they're just electric and magnetic waves. Gravitational waves, on the other hand, are oscillations in the fabric of space-time itself. So it's a completely different phenomena. That means you can't detect them in the same way. The electromagnetic radiation affects different particles differently depending on their charge and, I guess, to a certain extent on their mass, where gravitational waves, they affect all matter the same, regardless of whether it's positive or negative charge. The frequencies of of electromagnetic waves tend to start at about 1 megahertz and go up about 20 orders of magnitude, where the frequencies of gravitational waves start at 1 kilohertz and go down about 20 orders of magnitude. So it's like they're in the same range as like your hearing, but it can go much lower in frequency. And the neat thing about that is that, like, where we can think about astronomy and as you look and you see the stars, it's almost like there's an analog to hearing here. So it's like you don't see gravitational waves, you hear them. And I think it's like, I want to say it was Scott Hughes. He had a presentation on gravitational waves where he did the in-spiraling collision of black holes, but instead of just modeling on a screen what it looked like, he actually hooked it up to a speaker and you could hear it. Also, another thing is electromagnetic waves can be easily absorbed and scattered, where gravitational waves, because it affects all matter the same, you can't really scatter it. You can't really absorb it or scatter it. And also electromagnetic waves, they come from surfaces that are optically thin and gravity is weak, and gravitational waves come from things that are massive, compact, highly dynamical, really heavy objects. So what happens effectively is that electromagnetic waves are good for probing the visible parts of the universe. And gravitational waves are good for probing the dark parts of the universe. And it just so happens that like 90% of the universe is dark. We look at all the dark energy and dark matter. It's, this is actually most of the universe you can actually see with this. And so the astronomy is different. The tools have to be different. But the payoff is that we actually get to see a completely different part of the universe that we never could see before or hear. So conventional astronomy, to do look at electromagnetic waves, you have to have an electromagnetic telescope where you could have electromagnetic waves like light coming in and you observe it, or even a space-based telescope like Hubble or James Webb would have electromagnetic waves it would analyze, or you could have a big dish. But that's not going to work for gravitational waves. For gravitational waves, we're actually going to use these things called interferometers. And the first interferometers went online around 2002 and 2003. So they've been online for a while, although they most of that time was spent trying to get them working correctly, or get them working and understanding how they worked and improving the machines. So you could see that here's a map showing some of the gravitational wave detectors. There's like one that isn't on the map, and I think it's down in Australia. But that one, I think, is more of a it's more of a scientific test than it is an actual observatory. So it's not really expected to see anything. And you can see that here in the United States, we have the LIGO sites, which stands for Laser Interferometer Gravitational Wave Observatory. And we have two sites, one in Hanford, Washington, one in Livingston, Louisiana. So the one in Livingston is actually not even that far from here. Over in Europe, there's the GEO 600 project, which is a collaboration between Britain and Germany, and the VIRGO collaboration in Pisa, Italy, which is a collaboration between France and Italy. And then they're actually, when they built these LIGO detectors, they actually had 3 of them. The third one was actually inside the Hanford, Washington site, and they actually are planning to move that to India. So there will actually be a gravitational wave detector in India. And then in Japan, they're building this gravitational wave detector, which is underground and it's cryogenic. And it's expected to be extremely accurate, even with all the seismic noise there. So the neat thing about these is you really need to spread these out around the world, because if a gravitational wave comes in and you only have one detector, then how do you know that you're seeing a signal if nobody else can verify it? If you have 2 or more picking up the signal, then you can tell exactly where the signal is coming from. And you can also tell things about its polarization. So all these are very carefully planned where you're going to locate them geographically. So this is a cutaway of LIGO to show you how this thing actually works. The basic way that a gravitational wave does is it creates a strain. And a strain is basically a change in length over a total length. So it's a fraction of your change. So what happens with the LIGO is it shines a laser at this mirror, and then, or this beam splitter, and it splits the beam between these 2 different arms. So one goes up this way, the other one goes off 90 degrees. And it hits the mirror at the end, and it comes back, and it bounces back and forth between these 2 mirrors. It actually bounces thousands and thousands of times. And then eventually it makes it through, hits this photodiode, and gets recombined into a signal here. And the same thing happens along the other arm. So what happens is, if a gravitational wave were to come by, it would actually cause one arm to get a little bit longer and the other arm to get a little bit shorter. And the difference in the time the laser took to get between these two is going to tell you how much strain there was. And so the typical signal that we're expected to detect with a gravitational wave from, say, colliding black holes is on the order of 10 to the minus 21. That means that the change in length is 10 to the minus 21 of the total length. So that means if you want to detect a change of a tenth of a millimeter, you would need arms that are 3 light years long. Yeah. To get a tenth of a millimeter. Okay. Now, I think when they first brought that to NSF, they said, nope. So if you're ready to settle for, say, the diameter of an atomic nucleus, then that's 10 to the minus 13 centimeters, which is pretty tiny. That would require 4,000 kilometer long arms. Okay. I mean, I can't think of off the top of my head, but what's the diameter of the Earth? Yeah, so basically, that ain't even going to fit on Earth. So that's not going to work. So what they were able to get were 4 kilometer long arms. And with that, the strain that they're measuring, the delta L, is 1/1000th the diameter of an atomic nucleus. Okay. Okay. This is a single thing that explains why I'm not an experimentalist. Because when I was a grad student, I actually went out to Caltech when I was giving a talk, and I actually visited the LIGO lab, and they talked to me about all the, how they have to keep track of all the different sources of noise that can throw this thing off at 1/1000th the atomic nucleus. Like it could be everything from cars driving on the road. There's seismic noise. We actually did a study of this thing called gravitational gradient noise, where they can't even mechanically filter this out because it is actually gravitational waves that can be generated by the Earth because of just the changing densities of the magma within the Earth can actually throw this off. And so we looked at, there's this thing called a microseismic peak if you study, seismic waves, where about every 6 seconds a wave hits the shore of the United States or any other country. Only surfers and geologists know this because surfers have to know it because you catch the wave. But the idea is that translates into a frequency of like 1.6 hertz or something like that. And what that ends up doing is it would screw up any chance you have of putting a detector on Earth, which you can actually detect down to that frequency. So because of that, LIGO can't even see gravitational waves below a certain frequency because of all that seismic noise. And then you got other noise, like when they would hang these mirrors, they can't hang them from just ropes because it turns out the little fibers in the rope will make too much noise and that will destroy the signal. The lasers are not completely continuous. Like this laser might seem like a continuous dot, but what's happening is there's a slight variation in the number of photons. And that number of photons can actually throw off the signal. And then this is in a vacuum, but it's not cryogenically cooled. So, you can get any impurities in the vacuum that can throw it off. If the mirror is not perfect, that can throw it off. If the people walking by the mirror could probably throw it off. So there's a lot of different noise sources that you can imagine getting from this. So they built it anyway. This is the LIGO site at Hanford, Washington, and you can see that you see the mountains in the background. That's the best way to tell it's not Louisiana. So you could see that this is the main building, and you can see one of the arms and how long that thing is going off in the distance. This is the Livingston, Louisiana site, which is a lot more green. And you know, the interesting thing is with all these trees here, you know, you think about that question: if a tree falls in the woods, will LIGO hear it? And I'm guessing probably yes. But you could see here, you know, this is not a small site. I mean, this is pretty big. I don't have any pictures of the inside, but you could Google them. This is the VIRGO site in Pisa, Italy. So if anybody wants an excuse to fly over to Pisa, there's a gravitational wave site there. And you could see here, I mean, it's probably not far from a vineyard, so it's probably pretty good. This is the GO 600 in Hanover, Germany. And you could see, like, if you look at the central building here, this is a lot smaller than what you could see at either of these other sites. Like the LIGO sites have 4-kilometer long arms. VIRGO has 3-kilometer long arms. And GO 600, it's not even a kilometer, it's like 600 meters. So much smaller scale. But the idea of the GO 600, a lot of that is based around developing the technology, because it took them a long time to develop suspension devices. Like, if you know, a really interesting mechanical engineering problem was, how do you suspend this mirror in a way that it's not going to vibrate or shake or anything, and that all this little minor vibrations of the Earth are going to be completely dampened out. And those are the problems that they had to address. This is the one in Japan, which is actually under construction. This isn't actually up and running yet, but it's actually built underground, as you can see here. And part of that is, I guess, just shielded from different noise sources. But that's probably going to be one of the next ones that comes online. And then this is what LIGO India is basically going to be. I think this is basically the Hanford site from a different view, but you could see that it's still gonna, what they did was, within the LIGO, they had built 2-kilometer long arms inside of the facility. So there were the 4-kilometer arms, and then there was next to it 2-kilometer arms. And they're gonna take the 2-kilometer ones and send those to India, assuming everything works out with that plan. And then this is in Perth, Australia. So I believe this site is mostly for technology development. And these are small arms. I think they're like 80 meters or something like that. But you remember that what you can do is, by sending a laser beam back and forth, you can actually increase the accuracy, because it's like effectively creating a longer arm. Now, this is eLISA. Started off as LISA, and then NASA stopped funding it, so it became eLISA because the European Space Agency is funding it. And the idea here is that this is a space-based gravitational wave observatory. And what it is they have these 3 satellites, and they're flying in formation, and they're shooting laser beams between them. And they are a distance of 5 million kilometers between each arm. So it forms a triangle. Each one of these is 5 million kilometers. The nice thing about space is that, you know, you're not limited to the size of the Earth. So you can make longer arms. So then that way you can get, you know, more than diameter of an atomic nucleus between them. And also, another thing about being in space is that you don't have this whole problem with geological noise. So you can actually have this thing go lower frequencies than you can get with any of the terrestrial observatories. So basically, it will track behind the Earth probably by about 20 degrees, and it just follow the sun, and or follow the Earth in the orbit around the sun. And when it sees a gravitational wave, you could basically use either, you know, any 2 satellites can form effectively an arm. So it's like you have two arms here and a third arm here. So you can actually create your interferometer with a triangle as opposed to just having two arms. So the neat thing about this, like I said, is that you can go to lower frequency. So where the LIGO sites and the other terrestrial gravitational wave observatories, they can go from around 10 hertz to about 1,000 hertz in frequency, and their sweet spot is around 100. These LIGO or LISA can go down to like 1/100th of a hertz, up to like a hertz. So it's much lower frequency than you can actually ever get on Earth. And the reason why that's an advantage is because the more mass of the object you have generating gravitational waves, the lower the frequency of the waves it produces. So where you could see solar mass black holes with LIGO, this thing could actually see supermassive black holes, like the ones in the center of galaxies. And this is a new technique called pulsar timing. This is something else that they've been developing for years. The neat thing about this is that they actually can detect gravitational waves without actually having to physically build an interferometer. What they're doing is they're using pulsars as effectively arms at the ends of the interferometer. And what they're doing is they're setting up all these radio telescopes all around the planet. And they just have them just sitting there monitoring pulsars. And they'll monitor one out in this direction and one out in that direction and so on. And what they're waiting for is that these pulsars have to be really, really fast, like millisecond pulsars. And they just wait for a little glitch in how regular the pulsar is. Like one of them over here, we get the signal, it's a tiny bit earlier than we're supposed to. And the other one out there, we get it a little bit later. And from that, we could tell that there must have been a gravitational wave. And it warped the space-time between us, and it works. So the neat thing here is that you basically can create your interferometer using software and coordinating all these different sites all around the world. And then this is a new one that they're developing called the Einstein Telescope. The basic idea here is to take a lot of the lessons that were learned from LIGO and advanced LIGO and VIRGO and all the other ones, and create a gravitational wave interferometer underground. You can see it uses, it's a triangle, not just two arms, and so it can detect the gravitational waves and coordinate its own signal. By the way, part of the reason why they built LIGO in pairs was because they acknowledged the fact that you could get a glitch in one and that would show up as possibly a signal, and you could use the other one to kind of correlate that signal, so that if both of them are picking up a signal when they're spread out, then the odds of that being an accident are very low. So this is what basically the signals look like for each one, and you could see that this is LIGO, VIRGO, Advanced LIGO, Pranja. All of these, this is the noise curve for them. And so you could see that they're pretty much all between 10 hertz and 1,000 hertz. And then these are the expected, how accurate they need to be in order to see different sources. Like the binary black holes and binary neutron stars, pretty much all of them can see. But then if you get more accurate, you can actually see pulsars, you can see supernova, other sources. And then the eLISA would actually be able to see a much lower range. You could see below, I said 1/100th of a hertz. It's actually 10,000th of a hertz. And that can actually see supermassive black holes and and other sources from that. And then the pulsar timing is actually in the nanohertz range. that might actually pick up gravitational waves from the early universe. So why we need to know what these signals look like in advance. And one of the things is that before we could actually get the gravitational wave detectors online, we had to actually calculate what the signals were going to look like. Part of that was to justify the money it was spent on the detectors. Part of it was to understand what the observatories were seeing. Like we could model all kind of exotic stuff. And then if the detector sees it, then we know that we're right. But also we can test different theories of gravity. We can actually do science with this. So the idea was if you do the right modeling, then for all these sources, then you can, when you see something on the detector, you can just compare whatever the detector's seeing to that, and you know you saw something. Also, another thing is that the way LIGO works is that it's constantly getting these signals, and you know most of it looks like noise, and it compares that signal not just to the other signal coming from the LIGO site, but it also compares it to templates of all the different gravitational wave signals. And whenever it sees a match, it basically has an artificial intelligence machine learning algorithm going. That's when it alerts people, hey, you got to look at this. And then the scientists jump into action and start looking at the signal. So the whole idea is that we have to create these models so that the AI knows what to look for. So the thing about these signals is that few of them can be determined analytically. It's literally too hard of a math problem. We have to actually do numerical simulations, and this is where numerical relativity comes in. So basically, here is what the gravitational wave collision looks like for two binary black holes, where there's three phases to it. There's an in-spiral phase, there's a merger phase where they actually come together, and then there's a ring-down phase where it kind of becomes a spherical black hole. And you could see that in each phase, there's a different level of how much gravitational waves is emitted and the frequency and everything. Most of the frequency comes from this merger phase. Until around 2003, nobody was even able to calculate what this looked like. So it took a while to even figure out how to do that. And this is where you kind of create this template, and then the computer can look at that and say, well, this is what we're seeing. And so within numerical relativity, what we basically do is we start off with the initial conditions of what the space-time would look like, and it almost works like a movie. We take Einstein's equations, we break it up into the spatial equations and the time equations as separate things, and then at each instant, we'll solve what's going on, move it forward in time, solve it again, move it forward in time, solve it again, and have the computer continuously solving the solution. And in doing that, it kind of like it moves the movie forward. And so we start off with a solution that we know, like what the space-time around two black holes should look like. And we end up with the gravitational waves that emits. And so when we break this up, we got a lot of different equations we have to solve all at the same time. So this is what we do. This is where we solve it. This guys should look familiar to some of you. This is our singularity cluster that's located in this building. So you know, it used to be that in order to solve these equations, you needed a huge supercomputer, which cost like $5 million. And now we can solve a lot of this on this machine, which costs closer to $5,000. So, you know, that's progress. And that's also just showing you how advanced the computers got. By the way, Chuck, this is what your computer evolved into over time. So I want to show you another movie before we go. And this has to do with the merger of supermassive black holes. And so what's happening is we actually know the galaxies collide. And we also know from physics that in the middle of these galaxies, there are supermassive black holes. And so the neat thing here is that you put the two of those facts together and you could see that you're going to get supermassive black hole collisions or near collisions from these galaxy collisions. And also, whenever you have matter and it falls into the black hole, it's going to cause it to perturb and it's going to cause gravitational waves to be released. So you can see a lot of really interesting stuff going on here. Okay. So I think I already showed you some of these other movies. Oh, I didn't show you this one. This one was another movie about. This is another movie that shows the neutron star mergers in full general relativity. And so you can see that there's simulations. There's a lot of these out there, where some of them are black hole neutron star and some are neutron star neutron star. And you can see here the two neutron stars, they come together and this one is interesting because you can see they form these bars. So they're forming kind of oblong shaped neutron stars. And this is emitting a lot of gravitational waves. One reason I wanted to show you the neutron star collision is because I kind of hinted at this earlier when I talked about gamma ray bursts and where we didn't know where they came from. That turns out that's where a lot of those gamma ray bursts are coming from, neutron star collisions. And in one observation, LIGO detected a binary neutron star collision. And at the same time, they had their partners doing optical astronomy also watching, and they saw there was a gamma ray burst. And they correlate that together. They also found out that that's where heavier elements like gold come from these neutron star collisions. And they were able to also see the gravitational waves, how long it took us to get them to get to us, as the electromagnetic waves from the pulse of gamma rays came, and they saw that they move at about the same speed. So they proved Einstein's theory that gravitational waves move at the same speed as electromagnetic waves is true, or at least as far as we know, which shows that gravitons as a particle are massless, which is another big thing in Einstein's theory. So basically one observation and they proved three of the biggest mysteries in physics that nobody had any clue to. So that was a good day. So I think I already showed you this one. This was actually the binary black hole that they did observe. No, not that one. Yeah, this one. So you could see here, you got two black holes and they're spinning around. This was actually the first detection of gravitational waves. And so they created this simulation based pretty much exactly on the parameters they observed, where they saw two black holes that were roughly 30 solar masses each, and they merged. And they were about, I want to say they were about 3 billion light years away. And you can see that this is when they merged, and they got heavier and heavier and sink into a final black hole. So this earned them the Nobel Prize in Physics for 2017. Now notice, I told you before that Taylor-Haas, they detected that binary neutron star system in 1974, and they got the Nobel Prize in 1993. These guys they saw this first observation in September of 2015. Got the Nobel Prize in 2017. It's not a long wait. And actually, if you think about it, it's actually less than that, because even though the first detection was in September of 2015, they didn't tell the public until February of 16. So part of the incredible accomplishment of LIGO was that they were able to keep a secret among 500 people for 5 months. Yeah. Few people have ever accomplished such a thing. And so that confirmed, was a real confirmation of gravitational waves. It really opened up the field of gravitational wave astronomy. And it was really interesting because these guys have been working on this for 40 years. I mean, 40 years of working on this, doing science, developing the instruments, begging for money, and nothing, and seeing nothing. And then there was actually outside of Raynard Weiss and Kip Thorne, there was another guy outside of Barry Barsh who would have been the third guy for the Nobel Prize, but unfortunately he passed away right before before they actually made the detection, so that's why he lost out on it. But you can see here that 40 years, finally made a discovery, and then that was it. And I'm sure the day after they made the big announcement, everybody decided to sleep in. So in conclusion, this is an important part of modern physics that a lot of people don't know a lot about, because of the fact that we've only had detections of these for a few years now. I mean, it hasn't even been 4 years since the first detection. It's barely been more than 3 years since people even really knew about the first detection, actually had a paper to read on it. There's a large international effort. This is international physics at its best, because this is literally, just because of the geography involved, you can't even have just one country doing this work. And also, this is a field where you have theorists, you have computational people, you have the experimentalists all working together. So there's a lot of different parts to it. And and there's also a lot of creative stuff that people are doing, where they're actually using these observations to test fundamental theories of gravity, to look at the early universe, to be able to test alternative theories of gravity. So it's a lot of interesting stuff from that. So, questions? Yes?
So you're talking about the different size detectors being able to detect different frequencies. Large detectors can detect much lower frequencies. And those lower frequencies are associated with larger objects.
Right.
So is the idea that those collisions with those larger objects are louder, so you, for lack of a better word, so you'd be able to hear them from farther away as well? So you increase the amount of space you can observe?
Yeah. Like, for example, when they look at the range of LIGO, what they used to do was they use binary neutron stars in order to say that the range of LIGO is so many parsecs or something like that. And they would actually create a volume of space, centered on the Earth, where you could say, well, we can detect anything within this range. Now, when they found out that this whole binary black hole stuff wasn't just something we made up, that was actually something that could exist, then all of a sudden they started thinking about the range, not just in terms of binary neutron stars, but also binary black holes, because you could actually see them further away, even though they are, they're a little bit more massive. I mean, they're not like a million times more massive, but you're talking about on the order of maybe 10, an order of magnitude more massive. So you end up getting that much more range. And so if you go to supermassive black holes, like with LISA, when we were in grad school, we did a calculation on that. We found that if it meets the specs that everybody says it should meet. It should be able to see any gravitational wave in that frequency range in the visible universe. So literally, it could see as far as any telescope ever made.
Possibly farther because you can see past that 500,000 year
Yep.
wall.
Yeah. So it's really interesting. Yeah.
I don't know how accurate this is. If I'm wrong, tell me I'm wrong. But it seemed like after the first detection, then it was suddenly really easy to detect because they made all these detections afterwards. And it's like, how come it took this one? Did they like, revamp like the way they're doing their?
Oh well, it's actually a more interesting story than that. What happened was in September of 2015, they were gearing up LIGO and they were doing all the engineering stuff and they were getting ready to start their observing run. Because what they do is they do an observing run where they test out, where they're really looking for stuff, and they do engineering runs where they're just kind of tweaking the equipment and everything. The signal showed up while they were doing an engineering run. They weren't looking for it. So they were completely caught off guard, and a lot of people thought, is this a joke? I mean, were you messing with us? Because the signal was just too loud and clear to be anything but a joke. And they started looking around. Actually, I teach a class in the fall on this called on gravitational waves, and I actually use the book called Gravity's Kiss, where it was written by a sociologist who studies gravitational wave physicists. Kind of like Jane Goodall and the Apes. But so anyway, it told the inside story of a lot of this, and what happened was they weren't looking for a signal. They spent a lot of time confirming that it was an actual signal and it wasn't somebody playing a joke. There were not that many people who were actually capable of injecting a signal in that would show up on both sites, and so there was a lot that they had to do to confirm it. And also they had, for the first detection, you had to clear this hurdle of being over a 5 sigma standard, which basically means that the odds of it being something other than a gravitational wave were like 1 in a million. So what happened was that first detection was clear, and it was loud, and it was, unexpected and unbelievable. And then they had to actually freeze the detector in order to get the background information to prove that it was a 5 sigma accurate. And in doing that, they couldn't actually detect anything else. They didn't want to detect anything else. So they avoided that. And, and all this while they're doing all this stuff in secret and writing the paper and everything. And so after that, they had a few other candidate signals that came in that they sort of dismissed because they weren't at the level of accuracy they wanted. And then later on, when they got to the point after they released the information, that was when other people knew more about what to look for. And that's when VIRGO also started looking, and they could tell their astronomy partners to look at stuff. But they had basically written this whole protocol where until they had detected like 3 signals, they were going to go strictly by this protocol where information was very censored and didn't get out to the public. So I think once they got past the 3, then all of a sudden it was like, okay, we can just tell everybody whenever we think we see something. Okay. All right. Other questions? Yeah.
So you mentioned that the pulsar timing
Mm-hmm.
method can detect gravitational waves. So you said that it can detect a lot lower frequencies than the one that they're going to put out in space.
Right.
And I was just wondering why.
It's because the wavelength is so long. I mean, the arms are so long, effectively. Because in the case of like LIGO, I said that in order to get a 1/10 of a millimeter, you needed 3 light year long arms. Well, the distance from here to the nearest pulsar is a lot longer than 3 light years. So if you think about it, you've got a much longer arm, but also at the same time, if it takes that long for the signal to get between here and there, the wavelength is really long. And because the wavelength is really long, the frequency is really low. So you're naturally tuned to lower frequencies. So like a high frequency wave with the pulsar timing, it won't even show up as anything. But the low frequency is going to be really loud. So that's the theory on it. They haven't detected anything through pulsar timing yet, so we still got to see how exactly it's going to work. Okay, other questions? Yeah.
So we can see the waves. Have we had any luck like detecting the force carrier that gravitron?
No, because well, like I said, the problem with the graviton is like, I mean, the detected individual graviton, assuming it does exist, is even much harder than that. So the nice thing is that with that binary neutron star collision, they were able to find that the graviton, if it does, if you could write it as a particle, it does travel with the speed of light, which means it is a massless particle. So we got to learn that about it, but we're not quite at the level where we could do particle physics with it because that would require much higher energy. Okay. Yeah. Mm-hmm.
Like, is there anything else that could come from?
That's a good question. And the truth is that like we don't know. I mean, the thing, to get to that lower frequencies, it's got to be something really massive. I mean, more massive than a supermassive black hole. And also another thing that happens is that we know that as waves travel, like electromagnetic waves travel, they get redshifted. The same thing happens to gravitational waves. So it could be that it's a really low frequency, but like from the early universe, but it could also mean that it is it's a higher frequency that was redshifted from being so long ago. Like, I mean, if we saw something like a supermassive black hole collision from 17 billion years ago, that would be, okay, wow, we got to re-examine everything. So, I mean, but could that be out there? Who knows? Older than the known universe? Wow, that'd be interesting. So, I mean, so you never know. And that's the thing is that one thing that this really shows is how little we know about the universe, because only thing we know about is from looking at stars. And one thing we've learned from looking at the stars is that they only make up about 10% of the visible universe, when we start looking at dark matter and dark energy. So we don't really know much. And we have these dark matter halos around these galaxies. We don't know anything about them. We don't even know what the dark matter is. We don't even know what it's made of. We don't know if they're actually made of stuff or if it's just something about gravity we don't know because we don't know the theory well enough. So, I mean, yeah, at the end of the day, I don't know. I mean, we don't know a lot of stuff, so maybe what this will do is help guide the way. You had a question, and then you, yeah.
Do gravity waves still transfer energy like an
That's a good question. Yeah, they can, because in the Taylor-Haas binary system, they actually did take energy out of the system. And in the case of the binary black hole, they found, I think it was something like 3% of the mass of the black hole was transferred into gravitational energy. Yeah. I mean, there's probably some other things you can do with that, but yeah.
That was essentially my question, just kind of the energy they carry, what
Yeah.
exactly does a gravitational wave do? I mean, obviously
Yeah.
it's effective.
Well, yeah, it makes sense though, because I mean, it is actually taking particles and as they pass by, they're moving them. So it's doing something. Although, that's the stress and strain of space-time, and and from Einstein's theory, we know that. Actually, go back up here. We know from Einstein's theory that the curvature of space-time depends on this thing on the right-hand side, the stress-energy tensor, which is basically energy. So in order to get curvature in space-time, you have to put in energy. So that has to be in there somewhere. Yeah.
So outside of the detecting like gravitational waves, is there any application like space travel?
Not yet.
Not that-
Well, I mean, again, like I said, we're still trying to learn a lot because we don't know a whole lot about what else is in the universe. So, I mean, it could be that maybe there's some useful things that we can get out of that. It could be that, just learning about the universe. It could be that it tells us things about how gravity really works that might be useful in other ways in the future. So, we don't know yet. Stay tuned. But I mean, the neat thing is that anytime you're developing some type of science like this, it always ends up leading to kind of secondary inventions. And we saw that a lot with space travel. So what's happening here is uh, a lot of the things that they needed to develop in order to make LIGO work, like having a suspension system that filters out all of these vibrations, could be pretty useful elsewhere. A lot of the advances that we made in developing the computing and the simulations, we've learned things about how to do high performance simulations that other people weren't able to do in other fields because they weren't pushed as far. Because of the amount of data that had to be processed and simulated and the way it had to be done. There were things in terms of the artificial intelligence and the machine learning that are involved in this were pretty much state of the art. There was things involving the network in order to communicate between multiple sites in real time. There's probably secondary stuff like even just the, how do you get your 500 people on a conference call in a secure way and all that stuff. Just so there's, this is the interesting thing about physics is and science in general is that there's always this other stuff that ends up becoming really valuable. Like the whole reason why we even have a World Wide Web was because physicists didn't want to wait 6 months to see an article from their colleague. They wanted to be able to get the preprint now. And so they invented archive and the World Wide Web, and then we got that. So the neat thing here is that there's all these, I don't know, there's almost too many things I can even name. But actually, I remember I read a while back that somebody was actually trying to use basically this code or something similar to this code to try to model the stock market. So it could make people really rich or very, very poor. Probably both. Yeah. All right. Other questions? Yeah.
Like you say, gravitational wave is like polarized.
Yeah.
Like the
Oh, polarization. Um, the basic idea is, all right, when you have an electromagnetic wave, and like let's say you have polarized sunglasses, what happens is they have like little filters that go either vertically or horizontally. And what happens is when the light comes in, if the electric part of the electromagnetic wave is vertical, then it goes through the vertical parts. But if it's horizontal, it can't make it through the vertical part, so it gets stuck. And so you only, that's why polarized sunglasses, you put them on and you see about half the light. And another thing that can do is that, if you go to a movie theater and you see a 3D movie, what they do with the movies is that they actually polarize the movie on the screen so that your right eye sees one thing and your left eye sees something completely different. So they actually, and by doing that, they create a 3D effect. So what's happening here with gravitational waves is that they don't have a vertical and a horizontal polarization. They have a plus and a cross polarization. So this polarization here is like a plus, and this one is like a cross. And what happens is that they actually, if you actually, I don't have it on here, but there was a picture of the LIGO detectors where they're both basically forming L's, but they're orientated like this. So they're kind of off at different angles. And they did that on purpose because if this one is like a plus polarization, this one's like a cross polarization. And so if a plus polarization wave comes in, this one will see it stronger than the other one. And if a cross, then the other one will see it. And they can use that to determine the polarization of the gravitational waves coming in. Yeah, and also they can find the direction by looking at when the signals arrive relative to each other. So if one arrives a few microseconds later than the other one, then you can tell that. Yeah. Yes and no. You can actually get or you can actually get different polarizations within, like, I know within turbulence in like the early universe, you can actually see that there'll be different polarizations of the gravitational waves that'll come out because of the turbulence. But I think in terms of like binary black hole collisions, I think it has to do with the orientation of the plane of the binary black holes relative to each other. Yeah.
Does be attractive or repulsive like EM waves?
Kind of. Yeah, I mean, you could see here it kind of switches where they're sort of attracted here and then they're repelled. So they're being moved around. So when a wave passes by, it actually will cause things to move in either direction. But the thing is that like every piece of matter is going to respond the same. And actually, this was one of the things that we found really interesting when we started looking at the early universe and the plasma, was because if you can imagine if you have a plasma field where it's all charged particles, and it could just be sitting there just minding its own business. If a gravitational wave comes in, what that will do is it will actually cause the charged particles to move closer together or further apart, and that can actually generate waves within the plasma and excite the plasma, because it can actually cause the plasma particles to, basically they get closer together. They're more magnetically they're more attracted. They move further apart. They're less attracted. So it's changing the dynamics. And so one of the tests that we did on the plasma was actually injecting gravitational waves into the plasma, having it excite the plasma, and then seeing if how it excites the plasma matches up to how we expected it to. And that was how we could tell that the code actually worked. So that was also what was interesting to me, was that, like, thinking in the early universe, you had these gravitational waves like from inflation, and they were coming in and hitting this really dense plasma of the early universe, and then there was something going on. Okay. All right, other questions? Okay, that's it. I guess I'll see you guys next time. And if you haven't already, please turn in your papers, turn in the sign-in sheet, and let's see, next week, since spring break is over, there are no more breaks in the talks. Next week, we are going to have Margaret Chung here from University of Houston. Okay, let's see.